Today, we want to move on to triple integrals. If you didn't see this coming, you just haven't been paying attention to what's going on in this class. We do functions of one variable. We start upgrading by upgrading to functions of two variables. And that's what we've been dealing with these double integrals. Now we want to look at a function of integrating a function of three variables over some volume. The concept is the same. When we find the area under f and above I, we want to calculate the area, but the length is variable represented by the function. And so we have to switch to integration. If f of x is constant, we get to multiply the value of f of x by the length of the interval I and come up with area with multiplication. But since f is variable, we have to assume f is constant for some small change in the interval. Then we get to use multiplication. What we're doing is adding up values of the function. We're just plugging in all these values from the interval into the function and adding them up. It doesn't really make sense when I say it like that, because when we think of addition, we think of a plus sign in between a bunch of stuff. And here, the values from the interval are a continuum of values. So we're clearly doing something fishy. But the concept is we're plugging all these values from the interval into the function. We're going to be a little bit more Newton about it. Be a little bit timey-wimey in our definitions. The same thing is happening when we're finding the volume of under a surface and above a region. So I've got two-dimensional things, and I want the volume that's captured in between them. Functionally, we are doing the same thing. I want to calculate volume by taking the area and multiplying by the height. The area multiplied by the height. But the stupid height keeps being all variable. So we assume that the function is constant for small pieces of the region. Then we get to use multiplication, area times height. And we're adding up values of the function all over this region. We're taking all the x, y in this region and plugging them into the function. And that was our double integral stuff. If we just keep following this line to triple integrals, we're going to go from a function of two variables to a function of three variables. And now we have, instead of a two-dimensional surface in three-dimensional space, we have a three-dimensional solid in four-dimensional space. So we're going to get a four-dimensional volume. So it'll be like meters to the fourth power. It's hard for us to picture this, but we can still say it's going to be under the solid F and above the solid W. So we've got these two three-dimensional solids running around in four-dimensional space. And in between them, we are capturing some four-dimensional hypervolume. That's really weird to think about it. This is too early to think about stuff like that. So let's go take it back one step to how we make this calculation. We just take all the values from that three-dimensional solid and throw them into the function and add them up. It's the same thing that we were doing in double integrals. It's the same thing that we were doing in single integrals, plugging in a bunch of numbers into the function. Double integrals, we just had to figure out how to describe all the ordered pairs. In a triple integral, we're just going to have to figure out how to describe the ordered triples. Good news, everybody. We don't have to change what we're doing. Before, in our double integrals, our plan was, say, what's x between? What's y between? So our plan for a triple integral is just going to be the same thing. We're going to say, what's x between? And then we're going to say, what's y between? And since we've got three variables, we're just going to say, what's z between? Same thought process that goes on behind it. And mechanically, we're going to do the same thing. We're going to set up the triple integral with 3 integrals, one for x, one for y, and one for z. And we're just going to say what's the lowest value, what's the highest value. Let's describe this cube no, it's not a cube. Describe the rectangular solid. Let's describe the solid W with a triple integral. I realize that my pens are working better now because I actually did a better cleaning of the notepad. The reason that I mention this is because when I walk through a parking lot, if you've got bald tires, I am like 10 seconds away from writing a note and saying, dude, change your tires. Some people would say things like mind your own business, but this is my business, because if you're driving around on bald tires, you're putting all of us at risk. And it's like, dude, knock it off. You don't get to drive on bald tires, especially when I see some clapped out 90s Honda Civic on bald tires sitting in the parking lot. So I'm like, oh, great. That's not just a death trap for the occupants. That's out there to kill somebody. You know what I mean? And yet, I'm like, oh, why does my notebook not work? Because I haven't been maintaining it properly. So somewhere out there, there's some notebook fan. And he's like, oh, dude, it's not working because you're not cleaning it properly. So I finally changed my tires, is what I'm saying. Let's describe this the solid W with this triple integral. It's just a rectangular solid. Everything, the x, y, and z are all between constants. Oh. We can describe any order that we want. So let's just go in order. So dx. So we're going to start with the x's. And then we'll dy. And then we'll dz. This one's going to be really straightforward because I've used constants for all the boundaries. But the questions are going to be the same. And the requirements are going to be the same. The last integral has to be between constants. So we have to look for the lowest value of z and the highest value of z. And it looks like the lowest value of z is sitting here on the xy plane. And the highest value of z is going to be 3. So z is going to go from 0 to 3. Then we pick a value of z and think, what is y between? And because I'm being lazy, y is between 0 and 4. The lowest y value we see is 0. The highest y value is 4. And the highest y value is always the highest y value. So that's why we can go between 0 and 4. And finally, we do the x's. The lowest x value is 0. The largest x value is 2. So here's a triple integral used for integrating a function over this rectangular solid. In the case of double integrals, we always had 2 double integrals that we could use, a dx dy and a dy dx. With a triple integral, I have more. I can write these in whatever order I want. I can go dx dy dz, dx dz dy, dy dx dz, dy dz dx, dz dx dy, or dz dy dx. So we get 6 triple integrals to choose from. Of those 6, depending, this one is super simple, but if we start having functions running around, like if instead of the y's just being this y equals 4 plane as the largest value, I could write a cylinder or even just a parabola that goes up and back down again. In which case, one order might be better than the others. And we saw that yesterday in the integration process. We could, the problem that we had yesterday, we could not integrate with respect to y. We could integrate with respect to x, so we switched the order to do that. All right, let's recall some things, because I want to see that this triple integral stuff is really just building up from the double integral stuff, like even more than it already has. So let's recall some things. If we integrate the function 1 dx over an interval I, we just get the length of the interval. If we integrate over a region, the function 1 dA, that will give us the area of the region. Give you a few seconds to figure out what's coming next. If we integrate some solid w, integrate the function 1, let's see, I've gone from length to area, so I'm integrating little chunks of volume. If I integrate the function 1 dv over a solid w, that will give us the volume of the solid w. Now we get to encounter one of my favorite things to do in math class. Take a problem to which we already have the solution, apply the thing that we're talking about, and see that the thing we're talking about will produce the expected result. So we know that the volume of W is 2 times 3 times 4. So 2 times 3 is 6. Times 4 is 24. It's a little early for arithmetic. So we also know that we can represent the solid W as the area under the constant function z equals 3 and above the region where x goes from 0 to 2 and y goes from 0 to 4. Let's write the triple integral of 1 for this solid, and I want to do it in a particular order. So the volume of W from our problem, once again, we know that the volume is 24. The point is not coming up with the 24. The point is taking this thing and making sure it gives us the result. So I'm going to set up a triple integral of the function 1, and I want to set it up in this order. I want dz to go first. And I'm going to go dz, dx, dy. All we have to do is, since the x, y's, and z's are all just constants between pairs of constants, we just have to plug them in. So y goes from 0 to 4. In the middle, we have x going from 0 to 2. And at the front, we have z going between 0 and 3. So we are suspicious that, we know that integrating the function 1 dv, here's our dv, length, width, and height, is going to give us the volume of W. And we know that the volume of W is 24 because it's just a rectangular solid. We did length times width times height. Actually, I did height times width times depth. I didn't even use the length. That's all semantics. Let's actually make this calculation. Even though we know what the answer is supposed to be, let's make this calculation. So the first thing we'll do is we'll integrate the function with respect to z and then plug in from 0 to 3. And we still have this double integral from 0 to 4. X goes from 0 to 2. We integrate z. Oh, oops. Integral of 1 dz is going to be z, and we evaluate from 0 to 3. And we still have not integrated dx from 0 to 2. And we still have not integrated with respect to y from 0 to 4. And so we end up with this double integral. We plug in, I didn't leave myself enough space. We plug in the 3 and we plug in the 0 and subtract. So we're integrating the function 3 dx dy. Dx goes from 0 to 2, and dy goes from 0 to 4. We know that integrating the function 1 of this triple integral will give us the volume of the solid W. We did the first step where integrating dz, and we ended up with this double integral from 0 to 4 on y and from 0 to 2 on x, the function 3. Note that this double integral will be the volume under 3 and above the region from 0 to 2 on x and from 0 to 4 on y. So looking at this as a double integral, it's the volume under the 3 and above the rectangle. Our triple integral just led right to a double integral. Any questions? If we think of this the top here as the surface, we're finding the volume under this surface and above the region. And the region x goes from, in this region, x goes from 0 to 2 and y goes from 0 to 4, and it's a rectangular region. So our triple integral, once we start evaluating, led to a double integral. If we keep going, well, now we're going to integrate the function 3 and evaluate it from 0 to 2. So our last integral is going to be y from 0 to 4. The integral of 3 with respect to x is 3x, and we'll evaluate that from 0 to 2. So we evaluate 3x from 0 to 2. We get 3 times 2 is 6, minus 3 times 0 is 0. So this is just going to be the single integral from 0 to 4 of 6 dy. Once again, the 3x evaluated from 0 to 2 is 3 times 2 minus 3 times 0. So here we're integrating the function from 0 to 4 of 6 dy. This is going to give us our 24. But let's think about what this represents. What we have here is the cross-sectional area of 6, which will be the area of this face in the xz plane. X is 2, z is 6, so that area is 6, and we're just multiplying it by the height. So it all fits together, which is pretty awesome. I never plan things well. I always give myself lots of space at the top of the page, and then I end up cramming things in at the bottom of the page. It's like toothpaste compression. Like if your toothpaste is going to last 4 months, the first 90% of the tube is the first 3 months. Then the last month is at like the last 10% of the tube. It's just weird. Clearly, toothpaste does not exist in Euclidean space. Any questions? You know, I like big ideas, and I like to take a look at the big picture. It doesn't help us do problems, it helps us understand. And I care way more about your understanding of things than I do about your ability to, I don't know, do trigonometric substitution. Because I'd be willing to bet that even if everybody here has an A in Calc 2, if I gave you a quiz on trigonometric substitution like right now and didn't warn you, you'd be like, oh, yeah, I'm totally not going to look stuff up on the internet. And I'd be like, is that a keyboard I hear in the background? And you're like, oh, no, 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 I have a bird eating seeds or something. You know what I mean? And yet that's the exact assumption that math classes make. It's like, oh, well, we've talked about trigonometric substitution, so it should be no problem for the students that pass Calc 2. You know what I mean? All right. We're going to be spending some more time with triple integrals next week. The big idea is the same. We just want to plug a bunch of values into our function x, y, and z. We're just trying to describe all the x, y, and z that go in. And the idea is simple. What's the lowest x? What's the highest x? What's the lowest y? What's the highest y? What's the lowest z? What's the highest z? Just what are those three variables in between? Any questions? Comments? Deep thoughts? All right. That's going to do it for today. And that's going to do it for this week. Work on the first 3 assignments from chapter 16, which includes triple integrals, even though I've talked about them very little. It's okay. You're totally prepared for it. That's it for today. That's it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.